Dear students, so far we have discussed the particle nature of light and also wave particle duality. The beginning of 20th century witnessed a league of amazing physicists whose pioneering ideas took this world to a separate realm and set up the stage for the quantum physics to flourish. Now, if we start the century with 1900, in the year 1900, Max Planck developed the idea of representing light as discrete packets of energy. In 1905, Albert Einstein proposed light quanta that behaves like a particle in his famous photoelectric experiment. In 1913, Bohr constructs quantum theory of atomic structure. In 1924, de Broglie comes up with his idea of wave particle duality. In 1925, Pauli's formulation of exclusion principle. In 1926, Schrödinger came up with wave equation or wave mechanics. Then in 1927, Heisenberg formulates the uncertainty principle. In 1928, Dirac combines quantum mechanics with a special theory of relativity. Now, there is 30 years that shook the physics whole a lot, and it set up the platform for quantum mechanics to flourish, and after that many more ideas came forth to strengthen the arena of quantum mechanics. Now, what Planck said, that light deposits energy in terms of discrete packets. Each of these packets, energy packets, deposits an energy equal to h nu. These energies are called as light quanta. In the figure, if you will come across, there is a photon of blue light, there is a photon of red light, and that is a photon of yellow light. You can have the idea that all of them have got the same velocity, that is, they move with the speed of light, but what about their energy? They have different energy. It is the blue photon that has got the maximum energy because of the frequency of incident light, and it is the red photon which has got the minimum energy. Now, then came de Broglie with his idea of matter particles can have wavelength. They can exhibit wave-like behavior just like light can. So, de Broglie wavelength is given by lambda equal to h by p or h by mv, where p is the momentum of the particle. Now, with this idea, with this preliminary idea, in 1905, Einstein performed a famous experiment. When we shine light at a metal, it knocks electron out of the metal if that light has got sufficient energy. And perhaps I can say this is the experiment that has confirmed that a light has also got a particle nature, that a light can behave as a particle depending upon the experiment that we conduct. Now, what do we mean by that a light has got sufficient energy? What we mean by that? Light has got sufficient energy. This is like this, that suppose you will analyze a metal surface at a room temperature, you will find that a large number of free electrons moving upon the metal surface. Though they are free to move upon the metal surface, yet they cannot come out of it. The reason is that when they tries to come out of the metal surface, the positively charged ions tries to pull them back. The opposition offered by the metal surface to this release of electrons is known as your surface barrier. So, in order to make an electron come out of the metal surface, some additional amount of energy or some minimum amount of energy is required, and that minimum amount of energy required by an electron to just escape from the metal surface is called as work function of the metal. And this work function depends not only upon the nature of the metal, but also upon the condition of its surface. Now, this work function is measured in the unit electron volt and is denoted by a symbol called your phi or W0. Now, if we will come out of the concept of work function, what we will observe that what is the basically the concept of work function. Suppose think that this is a house in which there is a boy staying here. Now, he is not interested to go to his school. So, his teacher came up with an idea. He asked him that if you will come to school, I will give you an apple. So, here apple is the minimum condition that draws this boy out of his house to the school. Similarly, in order to make an electron come out of the metal surface, some minimum amount of energy is required, and that minimum amount of energy is known as your work function. It is measured in the unit electron volt, such that 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. So, depending upon the mode of supply of energy, this electron emission from a metal surface can be of basically 4 types. 1. Thermionic emission, 2nd. Field emission, 3rd. Secondary emission, and 4th one is photoelectric emission. Now, first come to the thermionic emission. In thermionic emission, what happens that here electron emission occurs due to application of a thermal energy. These electrons emitted here are called thermions. In case of field emission, the emission of electron occurs due to application of a highly or a strong electric field. This strong electric field drag these electrons out of the metal surface. Then comes your secondary emission. What happens here? An energetic electron strike the electron inside the metal atom, and it transfers some amount of energy to that electron, and if this energy is sufficient to overcome the surface barrier, this electron will come out of the metal surface. The ejected electron is called the secondary electron, and the electron that strikes, that causes this emission, is called the primary electron. Now, come to the 4th type of electron emission. This is the photoelectric emission, and which is the current topic that we are going to discuss in detail in this chapter. So, photoelectric emission is a phenomena by virtue of which electron emission occurs from a metal surface when a light or a radiation of a suitable frequency is incident upon it. Now, why I am saying that a light of a suitable frequency? Because only a light of suitable frequency will have enough energy to drag this electron out of the metal surface or to provide it the necessary work function. Now, the electrons emitted in the process are called photoelectrons, and the current thus set up in this circuit is called photocurrent. The metals from which electron emission occurs are called photometals. Generally, alkali metals and alkaline earth metals are suitable to be used as photometals because of their low work function. Because of low work function, they will require small amount of energy to come out of the metal surface. Now, let us discuss in detail about the experimental setup for photoelectric effect. Now, consider if we will analyze the figure, the experimental setup, you will find that this experimental setup consists of a glass chamber, a quartz chamber in which there is a window, and there are 2 electrodes there. There is a cathode there and there is an anode there, and anode is maintained at a positive potential with respect to cathode. Now, what happens here? When a light is allowed to fall upon the cathode, then and this if the light has also of a suitable frequency, then it causes the electron in the cathode or photometal to come out of the surface. And since the anode is at a positive potential with respect to cathode, these electrons starts moving toward the anode and thus set up a current in this circuit. Now, when we gradually increase this anode potential, what we will observe that the number of electrons reaching the plate will gradually increase, and so also the strength of photocurrent, and beyond a certain potential the current attains its saturation value, and that value of current is called saturation current. Later on we will came to know or we will discuss that this saturation current will only depend upon the intensity of incident radiation and not upon its frequency. This will only depend upon the intensity of incident radiation and not upon this frequency. Now, in order to reduce the photocurrent to its zero value, the anode potential is to be reversed. Now, the minimum anode potential at which the photocurrent becomes zero for a particular frequency of incident radiation is known as stopping potential, your stopping potential. Now, with this preliminary idea, we will now discuss how Einstein was able to demonstrate the photoelectric effect in particular, and we will throw light upon Einstein's photoelectric equation. Now, in order to go into the details of photoelectric equation, let us consider a metal surface. Now, consider this is a metal surface here with some work function say phi. Now, a light radiation of a frequency nu falls upon the metal surface. As the process is instantaneous, it causes an electron come out of the metal surface with certain velocities, maximum velocity, say V max. As per Planck's quantum theory, this light radiation consists of photons, each of energy E equal to h nu, where h is your Planck's constant and nu is your frequency of incident light or photon. As this energy falls upon this electron here, this electron will either absorb the entire energy of the photon or none of it. That means, either the photon will transfer its entire energy, but not a fraction of it. Now, what happens to the electron by gaining this energy? So, what happens here? By gaining this energy E equal to h nu, this electron here utilize this in two different ways. A part is utilized to provide work function to the metal, and the second part provides it certain kinetic energy, such that we can write that E equal to h nu and this E equal to, we can write this as phi plus k max. This shows that the energy incident upon the electron get utilized in two ways. A part is absorbed by the electron to provide it a necessary work function in order to come out of the metal surface, and the additional part of energy provides it kinetic energy. As a result, we can say that E equal to phi plus k max. That means what? We can say that if E greater than phi, then there is certain kinetic energy. If E is less than phi, no emission occurs, and if E equal to phi, then electrons just emitted with 0 kinetic energy. And with this idea, we will think of that how or what is we are now interested to find out what is the kinetic energy of the emitted electrons. So far we have discussed that the energy supplied by the photon to the electron in the metal are utilized in two ways. A part is used to provide it work function and the other part provides it necessary kinetic energy. Now, let us find out what will be the kinetic energy of this liberated electron. Now, we know that our E equal to your phi plus some k max. That implies we can write h nu equal to phi plus half m v max square, where the symbols have their usual meanings. When nu equal to nu 0, and what is this nu 0? This is the threshold frequency. This is the threshold frequency. And what is threshold frequency? This is the minimum frequency below which no electron emission occurs, or we can say in other sense, this is the minimum frequency at which electron emission just occurs with a 0 kinetic energy. So, we can write when nu equal to nu 0, k max equal to 0. So, if I will write this as equation 1 becomes h nu 0 equal to phi plus 0. Why? Because the kinetic energy has become 0. That implies I can write phi equal to h nu 0. That means work function of a metal is nothing but the product of your Planck's constant and threshold frequency. Now, substituting the value of phi as h nu 0 in equation 1, we can write h nu equal to h nu 0 plus half m v max square. That implies half m v max square equal to h nu minus h nu 0. That implies k max equal to half m v max square equal to h nu minus nu 0, and this is your Einstein's photoelectric equation in terms of frequency of incident radiation. Now, if we will derive the same, or if you will express the same in terms of your wavelength, then equation 2 can be rewritten as the following expression, that k max equal to h, in place of nu I have put c by lambda minus c by lambda 0. This comes out to be hc 1 by lambda minus 1 by lambda 0, where lambda is the wavelength of incident radiation and lambda 0 is the threshold wavelength. And remember it that this is the maximum wavelength that can cause electron emission occur from a metal surface. This is the maximum wavelength that can cause electron emission to occur from a metal surface. Now, with this brilliant idea, Einstein was able to explain the particle nature of light, or we can say confirm the particle nature of light, for which he has got a Nobel Prize in 1921. Rather, I can say that his work was so phenomenal that it explained the particle nature of light and the confusion relating to whether light can act as a particle or as a wave ends at this point. We can say that light can act as a particle or as a wave depending on the experiment that we conduct. Now, there is not only Einstein, there are several other architects who has pioneered his thoughts, his ideas to set up the stage for quantum mechanics. A few of them were Max Planck, your Bohr, de Broglie, Schrödinger, then you can say Pauli, then P.M. Dirac, Heisenberg, and lastly you can say Feynman. And Feynman, what is his contribution? He has derived the antiparticle of electron and named it as positron. Einstein was a versatile genius that he has not touched, or you can say that there is no realm of physics that he has not touched. Say, he has worked with your J.C. Bose, Satyendranath Bose to deduce Bose-Einstein statistics. We can say that he has devised that all the fundamental particles are devised or categorized into two types. One is boson and the second one is fermion. And under boson category there are photons and gravitons, and these bosons are integral spin particles that obey Bose-Einstein statistics. Now, Einstein was a beautiful violin player. He is a very good musician, and we can say that he is a very versatile genius. Einstein, though Einstein has got his Nobel Prize for photoelectric effect, yet we can say the most profound contribution of Einstein to this world of physics is the theory of relativity. We can say that he has proposed two theories of relativity. One is a general theory of relativity and the other one is special theory of relativity. General theory of relativity gives an idea of, you can say, the curvature of space. It gives us an idea to look at gravity in a way that we have never looked at, and this special theory of relativity, it tells us about how different phenomena change when something moves with a speed of light. Now, with this we can discuss certain conceptual questions, that how you will justify that the rest mass of a photon is 0. When a particle, we can say, when something moves with the speed of light, then the mass variation formula small m equal to m0 divided by 1 minus v square by c square. This m0 is the rest mass here. Now, you can say for a photon V equal to C. That implies this 1 minus V square by C square equal to 0. So, we can say M0 tends to 0. So, we can say what? That the rest mass of a photon is 0. What do we mean by that? We cannot have a photon at a rest. Photon is simply an energy radiation moving with speed of light. Now, come to the second question. Do all the photons have got the same mass? The answer is again no, because since they have got different frequencies, they have got different energies. So, though they move with the same speed, yet they have different masses. Next, the third question is, what happens to the energy of a photon if the wavelength of EM radiation is doubled? Then we can say that E equal to hc by lambda. When lambda becomes equal to 2 lambda, then this energy becomes equal to E prime becomes equal to E by 2. Light can have dual nature. It can behave as a particle or as a wave depending on the experiment that we conduct. There is an experiment, photoelectric effect, which we discussed earlier, which exhibits the particle nature of light. It was performed by Einstein, and Einstein proposed that when a light of suitable frequency is shined at a metal surface, it knocks an electron, it knocks electrons out of the metal, and the contemporary wave mechanics failed miserably to explain the experimental outcomes. But Einstein, with the help of quantum mechanics proposed by Planck, was able to explain the photoelectric effect and also predict the result that actually measured in the lab. So far, we have discussed that the energy supplied to the electron due to incident of light radiation is given by that E equal to, we can write this as phi plus k max. We have also deduced Einstein's photoelectric equation that k max equal to half m V max square equal to h nu minus nu 0, where the symbols have their usual meanings. Now, what about this nu 0? This is the threshold frequency. Now, with this equation, Einstein has gone to the extent of explaining stopping potential as well as to determine the Planck's constant from that concept. What is stopping potential? This is the minimum reverse potential on the plate or anode at which the photocurrent becomes 0 for a given frequency of incident radiation. When the electron in the metal or electron in this circuit is subjected to this stopping potential V0, it gains some kinetic energy given by your EV0 equal to k. From Einstein's photoelectric equation, we can write that this EV0 equal to h nu minus nu 0. That equal to h nu minus h nu 0. That implies V0 equal to your h nu by E minus h nu 0 by E. That equal to or implies V0 equal to H by E whole into nu minus H nu 0 by E. Rather, I will write this as a plus and here there is a minus and like this. So, in this equation, if this is y, this will be m, this will be x and this will be c. We can write this equation a representation of y equal to mx plus c. And what does this equation represent? This equation represents the equation to a straight line. So, if we plot a graph between v0 and nu, the nature of the graph is a straight line passing through the point minus h nu 0 by e on y axis and having a slope h by e. Now, let us plot the graph and see whether what is the nature coming thereon. So, by taking this v0 along y axis and your frequency along x axis, if I will plot the graph, this is frequency here and here there is your stopping potential v0, this is the positive axis here and this is the negative axis here. If this is the origin, the nature of the graph is something like this. And this point is your nu 0, the threshold frequency, and this is the point here. You can write this as minus h nu 0 by e. And if we will take the slope of this graph, then if this is theta, then a slope equal to your tan theta equal to your h by e. That implies h equal to e into slope. So, this is how you will be able to find out the Planck's constant from the concept of stopping potential. Now, let us come to the next idea, that how Einstein was actually able to explain the laws of photoelectric effect. This is the most crucial thing. Then Einstein has got a Nobel Prize for explaining the law of photoelectric effect. Now, I want to elaborate that how Einstein was actually able to put forth the laws of photoelectric effect and how he was actually able to explain the laws of photoelectric effect. Now, come to the law 1. Photoelectric effect is an instantaneous process. Photoelectric effect is an instantaneous process, that is, there is no time lag between the incidence of a photon and the emission of photoelectrons. Why? Photoelectric emission is the result of an elastic collision between a photon and an electron. The absorption of a photon by a free electron inside the metal is a single event which involves the transfer of energy in a single step. So, it involves no time lag because the photon will deliver its energy as a whole, but never a fraction of it. Now, come to the law 2. The number of electrons emitted per second and hence the saturation current depends on the intensity of incident radiation and not upon its frequency. What do we mean by that? If we will increase the intensity of incident radiation, there will be increase in number of photons that strike per unit area in 1 second, and the greater the number of photons striking per unit area, it will emit more number of photoelectrons per second and there will be increase in photocurrent. So, if we will plot a graph between intensity of incident radiation and your photoelectric current, the nature of the graph will be as follows. So, in this axis, say we have taken the strength of current and on this axis say there is intensity. The nature is like that. As intensity increases, there will be increase in your photoelectric current. Secondly, we can say that if we go on increasing this photoelectric or intensity of radiation, there will be a growth in saturation current with increase in intensity, but since stopping potential only depends upon frequency, that is why even if the intensity of radiation changes, the stopping potential remains the same. Why? Because we know that V0 equal to your h by E into nu minus h nu 0 by E. Since V0 is only dependent upon your frequency, and since frequency remains a constant, the saturation current remains the same irrespective of frequency of incident radiation. Now come to law 3. The maximum kinetic energy of the emitted photoelectrons and hence the stopping potential depends on the frequency of incident radiation and not upon its intensity. Now, what happens that when your intensity or frequency of incident radiation increases, we know that your energy of photon will increase. So, we can write that E equal to h nu, that implies E is a function of frequency. We know that your K max equal to h nu minus phi, where phi is a constant for a material. This is a constant for a particular metal. So, we know that this K max is a function of nu. That means what? That as the frequency of incident radiation increases, the value of energy of a photon increases, and as a result this maximum kinetic energy also increases. So, as this maximum kinetic energy increases, if we plot a graph between your maximum kinetic energy and frequency of incident radiation, the nature of the graph will be as follows. So, if this is the x y axis, in this axis I have taken your K max, and in this axis I have taken frequency. Remember one thing, so long as nu equal to nu 0, electrons are emitted with 0 kinetic energy. So, what happens here? This curve will start from here only. Why? Because at nu equal to nu 0, electrons are emitted with 0 kinetic energy. So, at this point nu equal to nu 0, K max equal to 0. Now, what happens below nu 0? See, we have written here that K max equal to h nu minus nu 0. This is the Einstein's photoelectric equation. If nu equal to nu 0 implies K max equal to 0. Nu greater than nu 0 implies K max greater than 0. That means it has a finite value. Now, let us think of that what happens when nu less than nu 0. Then K max will be negative, and negative kinetic energy does not have any significance. Now, let us see what does this graph or what more this graph represent. Now, let us take the slope of this graph. The slope of this graph, I can say that this K max equal to, I have written here h nu minus h nu 0. I can write this as h of nu minus some constant. That implies if I will plot a graph between k max and nu, the nature of the graph is a straight line whose slope equal to h. That means what? If I will plot a graph between k max and frequency of incident radiation, the slope of the graph will give the value of Planck's constant. Now, let us discuss the stopping potential as a function of frequency. Now, as the frequency of incident radiation increases, this stopping potential decreases. That means, you can say V0 becomes more negative. So, since the intensity of incident radiation is constant, with increase in frequency, the stopping potential gradually becomes more and more negative, but the saturation current remains constant at its value because the intensity of radiation remains constant. So, we can say that if we will plot a graph between here, that is stopping potential, say, or we can say this as your photoelectric current I, and this is the anode potential, this is plus and minus, then we will get a curve like this, where the saturation current remains constant, but the stopping potential, this is V01, this is V02 for nu 1 less than nu 2, and here the intensity is constant. So, with this we can say that stopping potential changes with frequency. Now, let us come to law 4 of a photoelectric effect. There is a certain minimum frequency of incident radiation called threshold frequency, below which no emission occurs, and this threshold frequency depends on the nature of the material. It is a constant for a metal and it does not change. We can say threshold frequency, it is the minimum frequency at which photoelectrons are just emitted with zero kinetic energy, and below which no electron emission occurs. Now, come to the expression k max equal to h nu minus nu 0. So, k max equal to your h nu minus nu 0. Now, if nu equal to nu 0, then nu minus nu 0 equal to 0 implies k max equal to 0. That is, electrons are emitted with zero kinetic energy. See the graph here. At the graph between k max and nu starts from nu 0, because for nu less than nu 0, the kinetic energy becomes negative, and this negative kinetic energy does not have any significance. Now, what follows next is a revolution. When we are talking about your photoelectric effect, then the idea of invention of photoelectric cell comes to our mind. Photoelectric cell is a device that converts your light energy into electrical energy, and when the idea of photocell comes to your mind, then suddenly the solar powered objects like your calculator, like solar powered street lights, solar powered your grass cutting machines, your solar cookers and many other things comes to in your mind. Now, the application does not stop here. The solar powered street lights, the solar powered your garden lights and solar powered light in our villages has created revolutions. Now, not only this, the march of solar energy has come to this extent that it has powered our homes. You can have a visualized effect, or you can have the image of solar powered homes in which all necessary utensils, all necessary appliances are run by your solar energy, say it be your air conditioner, say it be your cooker, television, anything else, it is running on solar power. Now, this revolution does not also stop here. This solar light also used to provide energy to the satellites. So, satellite by using solar panels also consumes solar energy for their activities. The revolution of solar panelled lights or revolution of solar energy not only changes the life throughout the world, it has also changed the life in Odisha itself. You remember one name, Baripatha, a village some 30 kilometers from the outskirts of Bhubaneswar that has become the first entirely solar powered village in Odisha from 2nd October 2015. Starting from every utilities, every activities in that village is run by your solar power. So, this solar power has created a revolution. This has created solar power lights, solar power activities and solar power villages in our country. So, definitely this solar energy has become an alternating source of energy, which is a renewable source of energy which causes no pollution. So, governments and different agencies are giving stress upon the fact that these solar photo cells or solar panelled utensils should be used more and more. Now, with this, let us come to certain numerical questions. The first question, a light of wavelength 6000 angstrom falls on a photosensitive metal plate of work function 1.9 eV. So, determine the energy of the photon in electron volt and kinetic energy of the photon and its stopping potential. So, I will not go detailedly into solving this question, rather I will give some hint to solve these problems. Let us see that what is the data that it was given. Wavelength of light is your 6000 angstrom, and this is nothing but 6 into 10 to the power minus 7 meter. So, the energy of each photon E equal to hc by lambda, where h equal to 6.626 into 10 to the power minus 34. This is 3 into 10 to the power 8 meter per second, and this lambda comes out to be 6 into 10 to the power minus 7, and this answer will come out in joule. So, this is the energy of the photon in joule. Now, we can easily convert it into electron volt, that 1 joule equal to 1.6 into, or 1 EV equal to 1.6 into 10 to the power minus 19 joule. Using this concept, we can convert this joule into the corresponding value in electron volt. Now, kinetic energy of the photoelectron. Now, kinetic energy of the photoelectron, your K max equal to your E minus phi. Now, putting the value of E from here and taking the value of phi as 1.9 eV, we can easily calculate what is the value of this kinetic energy. And so far as stopping potential is concerned, that this EV0 equal to, we know that E minus phi, and which is nothing but K max. That means the value of K max here is nothing but the value of E V 0. So, that implies V 0 equal to K max by E. Now, come to the next question here, that the work function of a certain metal is 4.2 eV. Will this metal offer photoelectric emission for incident radiation of wavelength 300 nanometer? Then the answer is simple, that you first find out, taking the value of lambda as a 300 nanometer, the energy of the photon will be E equal to hc by lambda. Convert this energy into corresponding value in electron volt. If the value of energy is equal to or greater than 4.2 electron volt, then electron emission will occur, and if this is below 4.2 eV, then there will be no electron emission. Now, come to the next question. Can X-rays cause photoelectric effect? X-rays are high frequency radiations. So, the energy of one X-ray photon provides enough energy to an electron to cause photoelectric emission to occur. So, the answer is yes, with X-ray light your photoelectric emission will occur. Now, out of microwaves, UV rays and infrared rays, which radiation is most effective for emission of electron from a metal surface? It is the micro UV rays, because of their high frequency, is most suitable for emission of electrons, as it provides enough energy. Thank you.